Well, so I wrote this talk with a mixed audience in mind. Last year I gave a talk on exoplanets, and the majority of the audience were school kids. So I thought maybe there'll be school kids here again and their teachers. I don't think I see any school kids. I see one of my old primary school friends who we became reunited just in the last few weeks after 50 years of being separated. So that's Suzanne, I don't know where she's sitting, there you are. So, and we have people from the Astronomical Society of Victoria. I think we have some people who are attending an astrophysics conference here. So we have a range of backgrounds, but I always like to remind people of a quote from Enrico Fermi. Never underestimate the pleasure people get from hearing things they already know. So you may have heard some of this before from me if you've come to previous lectures on exoplanets. But tonight's focus really is the Nobel Prize in Physics, or at least half of the Nobel Prize in Physics. And I don't know, I guess if you're here, you have taken some interest in this. It's an interesting citation we see here for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. Okay, so there's two things there, and we'll see the two things in a sec. But as with all these prizes, there's always some political intrigue going on behind it, and if you're interested in that, you can ask me about it at the end. There's even some gender politics in there. Wow, so cool. Right, so that was the main citation, but actually I like this quote from the Nobel Prize website. Their discoveries have forever changed our conception of the world, and that's what unites these two halves of the prizes. The first part of the prize went to James Peebles from Princeton for his work in physical cosmology. So cosmology, the universe at large and its evolution. And on the extremely opposite scale, length scale, the other half of the prize went to my colleagues Michel and Didier Queloz from Geneva for their discovery of an exoplanet orbiting a solar-type star. Okay, they bothered to say orbiting a solar-type star. I think I mistakenly wrote main sequence star in the abstract. I meant to change that to be a bit clearer. Stars like our sun. Now, in fact, one of Bernard and my colleagues discovered planets around a dead star 3 years earlier in 1992, Alex Volchan, and that's part of the intrigue, the politics. Why wasn't he on the list? And he hoped that he would be. But the thing is that really this discovery made by Didier and Michel is momentous because it tells us that the solar system is not the only planetary system like ours in which you can live, which can harbour life, as we didn't know if we were alone or not until 1995. So and in particular, the field has absolutely exploded and involves everybody, all the fields of science, from geology to atmospheric science, mathematics, biology, and so on. It's really changed the face of science, this discovery. So I want to give you a feel for this. So I'm going to give a little bit of an historical account to give you a feel for why it's so important. And also why it took till 1995 to make this discovery. So before 1995, for all we knew, we were alone. Well, of course, there are other planets in the solar system. We knew there was more than one planet, but certainly still today we don't know of any other planets or any other place in the universe that harbours life. People are certainly working hard on that. Yes, that's it. So there's the solar system, and so of course we well, some of us still like to say we have 9 planets. I'm still very fond of Pluto. It's very little though. But nonetheless, we didn't know whether that was all there was until 1995. And now, well, in 1995 we knew just one other planet, and it's important to realise that is a Jupiter-like planet. We'll come back to that, a big planet. But now we know, thanks to the work, especially of the Geneva people, but of people all around the world, we know that at least 40% of stars, we're statisticians, in the universe, well, we haven't studied all of them, but we've studied lots of nearby stars, and we can infer that most stars, or at least half of stars, harbour planets. So this is, and you might say, well, yeah, well, of course. You know, it's like asking, well, do you believe life exists elsewhere? Well, I don't know, but I just feel it just has to be true. But actually, I'll tell you a little story about why, and Michel Mail reminded me of this. People old enough even remember this, people in the field, I mean. And that is the theory of planet formation. How do planets form? Well, we didn't know. We've got a pretty good idea now, but as recently as the 70s, well, actually the 80s, when I was doing my PhD, we still took seriously what's called the capture hypothesis. And the idea was that 2 stars, well, a star, another star, came close enough to our sun for some material to be ripped off. Well, they probably ripped a bit of, in the idea anyway, ripped a bit off from each other. Here's my scrappy drawing. Materials ripped off the passing star and it continues on its way, but from the material that was ripped off, planets formed. Okay, so that's the capture hypothesis, and it was certainly still taken seriously in the 80s when I was doing my PhD. Yes, I look here. The problem, well, the thing about a consequence of this formation hypothesis is that planets would be very, very rare. That's because stars are very, very far apart in most places in the universe. For example, the average distance between stars in our neighbourhood is 20 million sun diameters. And so I had the potential high school students in mind, who aren't here, but I can say it to you anyway. I give the unit of distance as in sun diameters, because, and this is how astrophysicists learn to think. This is how I was teaching my honours student, Daniel, sitting up there, how to think. We think in relative terms. If I want to think about the likelihood of 2 stars passing close to each other, I want to think in terms of the size of those stars, not in terms of kilometres or metres. If I told you the distance in metres, it would just be some great big number that's meaningless. Well, this is a great big number anyway, and it tells you that stars are super, super, super far apart. So, therefore, planets would be super, super, super rare if this is the way planets form. The other main hypothesis at the time is called the planetesimal hypothesis. And a Russian scientist called Safronov came up with this idea that, well, we had a pretty good idea that stars form from interstellar clouds. Gravity causes part of the cloud to collapse, and clouds themselves have some kind of spin, angular momentum we call it, and as the cloud shrinks under gravity, that cloud would spin up and a disk would form. So his idea was that from this disk swirling around the star that's attempting to form in the cloud, material would accumulate into planets. And there's an artist's depiction of that process. So, but we still didn't know, well, which theory was the good one, until a few years later, in the 80s, the first protoplanetary disk was observed. So this is a real picture of a dusty disk around the young star Beta Pictoris. And we're seeing it edge on. You know, you might see, and I'll show you a picture of another disk that we see almost face on. But this was the first protoplanetary disk, and this was confirmation of the idea that disks form around stars as they form, and the planetesimal hypothesis of Safronoff became the paradigm, we call it, you know, the accepted theory of planet formation. Of course, there are lots of details to fill out, and people are working very hard to do that. But the general idea holds. Here's a picture, a recent picture of a real protoplanetary disk made by using the telescope ALMA in Chile. And you see all the dishes there, and we see very high resolution, and we see gaps and rings and so on, and so we're getting a better and better look at how planets form, and we've even starting to see the presence of planets in these disks. Okay, now another important part of the story, of the Nobel Prize story and the story generally, is how planets like Jupiter form. So remember, the first planet to be discovered was a Jupiter-like planet. And the thing is that our theory, we still believe this, that planets like Jupiter need to form far away from their star. Now, our Jupiter is 12 times as far away from the Sun as the Earth. So we call this unit of distance an astronomical unit. So Jupiter is 12 astronomical units from the Sun, and baby, it's cold out there. It's really cold, and ice, water in the form of ice, water happily exists in ice form out there. And these protoplanetary disks have a lot of water in them. And they also have a lot of dust. You know, the Earth is a rocky planet, and basically it's just a whole lot of dust stuck together. But the further away from a star you are, the more ice, like the planets further out in the solar system tend to have a higher water ice content than planets closer to the Sun. So the idea is you've got all this water in this protoplanetary disk, and you've got a lot of dust, and you know what happens when you've got a dust storm and it's very cold in the atmosphere. The dust seeds hail. So you've got all this hail, this ice, forming and sticking together and making a bigger and bigger planet core, we call it. And this happens, we believe, very quickly, while lots of gas is still around, and this icy planet core accumulates or accretes, we call it, very quickly gas to become a gas giant like Jupiter. Jupiter's 3 times the mass of Earth, 300 times as heavy, and 10 times the size. So it's a whopper. And that's important for our story too, that it's very massive, because as we'll see, we need lots of mass to do our detection, or certainly Michel and Didier did. So the message from this is planets like Jupiter need lots of ice to form. They cannot form close to their stars because it's way too hot. Ain't no ice right near the Sun or any other star. So a few years after the discovery of, in fact 12 years after the discovery of Beta Pic, a Jupiter is discovered orbiting the Sun-like star 51 Pegasus. And there's Didier and Michel from back in those days, and there's the observatory that they used to discover this planet. So the crazy thing about it, and the thing that really threw them and threw the astronomical community for a six, was that this planet takes only 4.2 days to orbit the Sun, its star. And so they're thinking, this can't be right, this can't be right. And you'll see how they did it in a sec. But they thought, well, everyone told us that such a planet can only form far from its star, where there's lots of ice. And these guys thought they were going to be in for the long haul, having to wait for 12 years or so, for a long time to see the effect of one orbit of a Jupiter-like planet. So they got lucky big time to see this thing. But how the hell did it get there? Why? What was that ice, this gas giant doing so close to its star? Now, here's a little tiny piece of one of my favourite films about this story. And I don't know if we're going to be able to hear it, because Steve, we're a bit sort of unsure about our equipment here. Let's give it a try, and if we can't hear Didier talking, then we'll move on. Let's give it a go. This is the dear little village where the observatory is.
Each time they looked at the star, they plotted its speed on a graph. And each time they looked, the speed had changed. Every visit to the observatory gave them more data, and eventually a pattern emerged. When they looked at the graph as a whole, it showed a wobble. By March 1995, they were confident they knew what 51 Peg was up to, and believed they could predict its every move. Just as they were ready to test their prediction, they ran into a problem.
And then, as the sky is moving, you cannot observe the same star during all the year. And then the star we could not observe that stars after March. And we had to wait up to July. And then we had the curve, the wobble, we had a prediction, but we had to wait.
And there they are waiting, that's right. There's a really nice BBC film made back in the day. Okay, so why did it take so long to discover planets around other stars? So I'm going to tell you about the method they used to detect that planet, and since then, hundreds of other planets. And then, and I'll say briefly about another method that's been very successful. Why did it take so long? Okay, so the sun, first of all, you have to realise that we don't see these planets directly. There are a handful of planets that we can see directly, but the thing is, if you're trying to see a planet, say like Jupiter, it's like seeing a firefly in the halo of a lighthouse lamp. The sun is 1 billion times as bright as Jupiter in our solar system, and the light that we see from Jupiter is mostly reflected light, unless you look in the infrared, that's another story. Okay, so we usually cannot see planets directly. So another thing to get a feel of is the relative, well really what matters is the mass, the relative mass of the star and the planet you're trying to detect. That is for this method that they used for this first discovery. Later on I'll talk about the size as well. But this, well, we see that the sizes, the sizes of the planets here are to scale. Their distances aren't to scale, so that gives us a feel. But the sun weighs 1,000 times as much as Jupiter, and that's really important for the story. So the method used to detect the first extrasolar planet, and hundreds after it, is called the radial velocity method. And this method relies on, it's an indirect method of detection. So we're not seeing the planet directly, but we're seeing the effect of the planet on the star. And it's kind of like one of these hammer throw people, you know, when they're spinning the thing around their head, this heavy ball, they themselves kind of move in a circle. They're actually moving around the centre of mass of the two objects. So for us it's a star and a planet. The planet is orbiting around the star, and it makes the star wobble around the centre of mass. So what astronomers do is they stare at a star hoping to discover a planet this way, and they disperse the light. Well, for example, if you shone white light through a prism, you would see a little rainbow, right? They use some things called gratings, but nonetheless, the same kind of idea. And on top of this rainbow, this spectrum, there are some dark lines. They're called absorption lines, and they're characteristic of the gas, like a barcode. A characteristic of the atoms present in the gas. Mostly planets and, well, like Jupiter, and stars are mostly made of hydrogen and some helium, and there are other elements in there. But so this forms a barcode. But the thing is, when the object is moving, or the star is moving, this barcode moves back and forward. It's like, well, it's called the Doppler effect. If a truck is moving away from you, you hear it go, and this is the sound wave stretching out as the truck moves away. If it moves towards you, actually the sound waves compress and the frequency goes up. So the same thing happens with light. And so if you've got a planet, well, if you've got a star wobbling due to an unseen planet, then sometimes the star is moving towards you and sometimes the star is moving away. And so this little barcode moves back and forward with a period equal to the orbital period of the planet. And this is how Michel and Didier discovered this first planet. They were staring at lots of stars, hoping to see something, but like I said, they thought they'd have to, that little plot that we saw on the movie, they thought they'd have to wait 12 years to get it to curve around. But they only had to wait, well, they had to wait 4 days, but they wanted to look at it over many lots of 4 days and check that it went up and down and up and down. And Didier was talking about in there that, you know, stars, you can only observe stars when they're in the sky at night, and you know, stars set like the sun sets and go below the horizon, and you can't observe them for some time. Some stars are in the sky the whole time, but this one certainly wasn't. So they figured gee, this thing seems to be wobbling up and wobbling back and forward every 4 days, but you know, is it really happening? We've got to come back after some months or however long it was and see if they can predict where the next point on the curve would be. Okay, so in fact, nearly 1,000 of the 4,000 planets known so far have been detected this way, and this was the main way of detecting planets for quite some time. Okay, well, there's a little animation of this Doppler effect. We see that the light goes red and blue, it's sort of an exaggeration, and the stars certainly don't wobble that much unless another star is orbiting them. Then they wobble a lot. But this is just to give a feel for it. Oh, I've gone past. Where's that little thing? Yeah, okay. So you saw that the little dots on the movie, and what they were doing was plotting this. So there's a nice little formula for people who like looking at formulas, like me. If you can measure that little shift of the barcode back and forward, you could measure the shift in the wavelength compared to what it would be if it wasn't moving. That's this thing. Where's my arrow? My arrow. We can't see the arrow on that, Steve. Doesn't matter. This delta lambda here, nice Greek symbols. I love Greek symbols. They make me feel good when I look at that. Delta lambda over lambda naught, the wavelength in the rest frame, the laboratory frame, happens to equal the speed of the thing you're observing divided by the speed of light. It's very beautiful. So if you can measure this, you can work out that. And that's what this plot is, and that's what we saw on the little movie. And you can measure the period as well. Actually, this is a bit of a scrappy drawing. I mean, normally you'd have time, just time, normal time, in days on the x-axis, and the time between the minima, the dips, would give you the orbital period. And the radial velocity in this case it's in kilometres a second, is on the y-axis. So you can measure how fast the star is wobbling. Now this example is an exaggerated example. That's what you'd see if you had a star like the Sun and a thing orbiting it that had 1/10 of the mass. And if that was happening at the distance that the Earth is from the Sun, it would be moving at 10,000 kilometres an hour, which is, well, it's a lot. I should have worked out what it is in seconds, and metres per second. The mass ratio of Jupiter to the Sun is 1,000th, like I said before, and if you put Jupiter at the position of the Earth, it would move at 100 kilometres. It wouldn't move at 100 kilometres. The star would move at 100 kilometres an hour in response. Now, 100 kilometres an hour is as fast as you probably drove coming on the freeway tonight. So that's not very fast as far as astronomical bodies go, and this is why it was so hard to detect the first exoplanet, because they're measuring tiny, tiny speeds. As for trying to detect an Earth planet going around a star like the Sun, the Earth makes the star wobble at a measly 9 centimetres a second. I can move my hand that far, just like that, poof. So, and we're trying, not me, but the observers are trying to have built instruments to actually measure such measly speeds to try and detect planets like the Earth orbiting stars like the Sun. And of course, if the closer the planet is to the star, the bigger the wobble. So it helps that if you have short periods, they make bigger wobbles. There's the radial velocity curve of 51 peg, and actually this curve was made by some competitors in America, and that's part of the intrigue and the whole story that I alluded to earlier. I should have put their little plot. Oh, I know I didn't. That's all right. Okay, so radial velocity amplitudes, the size, the size of the signal, as I said before, it depends on how close the planet is to the star, and it also depends on the mass of the planet, right? So the guy with the hammer throw thing, if he just had a peanut on the end of his rope, well, he wouldn't move, like it'd just be pathetic. But the heavier the thing is, the more he moves. And so there's the mass of the planet making the star wobble, and how close it is determines the size, well, the mass and the closeness or the distance of the planet determines how the wobble. So we see up the top, if we put Jupiter at, well, a 20th of an AU, so that's like 51 peg, something like that. 20th our distance from the Sun, much closer than Mercury. Mercury takes 88 days. See, you want relative numbers. Daniel knows that, don't you, Daniel, up there? Everything's relative. You've got to think in terms of relativities. So if I, put Jupiter close to the Sun, I get the signal that the guys measured, something like 50 to 100 metres per second. If I put Jupiter further out, it goes down. I've got 28 metres per second there, and so on. The further away it is, the smaller the signal, the harder it gets to detect. Okay, they're big guys like Jupiter. Jupiter's the monster in our solar system. Neptune is, well, it's 17 times the mass of the Earth instead of 1,000, instead of 300 rather. So it's Neptunes are much harder to detect. And as for Earth's, well, Earth's down the bottom there, I said 9 centimetres a second. There's these things called super-Earths in between. So Uranus is like Neptune, okay, so we call those ice giants. And Jupiter and Saturn are called gas giants. But there's these things the astronomers have discovered in the meantime called super-Earths, and they're like 5 to 10 times the mass of the Earth, they're rocky. See, Neptune and Uranus, well, they have big rocky ice cores, but they have a thick, dense atmosphere on top. So they're kind of in-betweenish kind of thing. So super Earths are things that don't exist in the solar system, and we've discovered lots of those. Okay, so why did it take till 1995 to do this? Well, I sort of mentioned before, you've got to be able to measure these tiny motions of the stars. Astronomers have been able to measure, use the radial velocity method to measure the motions of binary stars for 100 years. So if you've got two big things of similar mass moving around each other, they make a really big shift in that spectrum, and it's very easy to measure. But these planets are a different question. Okay, all right. Well, so the Geneva guys got to work making, well, they used a spectrograph so a spectrograph's the instrument they use to disperse the light to get the spectrum that we saw before. And then they made their own, put it on their own telescope in Chile, and went on to do surveys, stare at stars, night after night, whenever the stars were up, and try and detect these wobbles. And after 10 years after the discovery of 51 Peg, so we're talking about mid-2000s now, about 200 exoplanets were known, but they were all Jupiters and Saturns, because the spectrographs that they were using weren't, didn't have the sensitivity, high enough sensitivity to detect anything smaller or less massive. And here's a bit of a daggy old plot from the day, but it tells us a lot actually. So this is the planet mass distribution. So remember, we didn't know anything about what was out there. Nothing. Like, this is 5 minutes ago. If you're old enough, it really feels like yesterday. 1995, yes. Both my kids were already born, so there you go. That's yesterday. Here is a plot, yes, so we've got the number of planets. So this is a distribution. On the x-axis, we've got planet mass in Jupiters, in units of Jupiters. And what this tells us is there are many more, planets like Jupiter are much more common than more massive planets. So we go up to 24 Jupiter masses here. There's real whoppers, but still much less than a star. But this curve is quite smooth, really. It tells us that nature is making many more smaller planets than bigger planets. Okay, but they're still Jupiters, big monster planets. What about, these my arrows, what happens down here at lower masses? Does the distribution keep going up, or does it go down? I mean, these were the questions people, and still are the questions that we want to know the answers to. What's out there in the gloom? That's why I showed the picture at the beginning with the Earth sitting there in the black. I mean, we really were just there in the gloom all by ourselves. What's out there? And we know so much more now, and this is why the whole thing is worth a Nobel Prize. What's that telling me? The beautiful Harp spectrograph. So again, the guys at Geneva, and in collaboration with people from other countries, but they designed and built this instrument in Geneva. It's called Harp's High Accuracy Radial Velocity Planet Searcher. They dream up the acronym first and then try and fit some words to it. Yeah. No, because there's stories with that. Okay, now this, I've taken all the technical detail off this. I gave a talk about this in our department the other day, and so I had much more technical stuff there. Here's the amazing thing. They are wanting to, and this thing's been operational since I think 2003. They put their spectrograph inside a vacuum, in a vacuum tank. And the reason for that is, so 1 metre a second, okay, here's 1 metre, with my hand. I mean, really you have to appreciate they are trying to measure wobbles of stars that tiny. And in fact, I'll show you, well, I don't know if I've got the slide. They've now built a spectrograph to put on the VLT in Chile, the big telescope. It's in Chile that can measure down to 9 centimetres a second. So they're really, really after the Earth's now in the habitable zone. But anyway, this thing, so yes, they put the spectrograph in a vacuum because any temperature and pressure variations will mimic a radial a velocity, will look like a velocity. And I put that formula up before with the wavelength, the delta lambda on lambda. We measure wavelengths in angstrom, 10 to the minus 10 metres. And so, okay, 10 to the minus 10 metres. Okay, that's 1 angstrom. 1 metre a second produces a change in the wavelength of 10 to the minus 5 angstrom. 10 to the minus 15 metres. This is what they're trying to measure. Now, how the hell, I mean, come on guys, that's just nuts. Well, it's certainly true that you can't measure the shift of one of those lines that I showed you, the dark lines, by itself at that precision. But what they do is they look at the spectrum of the star and with thousands of lines, and they compare that spectrum to another spectrum that's, a reference spectrum they call it, well, it's a long story, but they can detect, basically they're tracking the motion of all these lines, and statistically, you can, people who know about the central limit theorem, statistically, even though you can't measure one, you get the average shift, and you can actually measure shifts in wavelength at this ridiculous level of 10 to the minus 15 metres. Holy moly. Okay. So these high precision spectrographs allow us to detect planets like Neptune and Uranus, the super Earths I mentioned before, so there's, like in between Earths and Neptune, say 5 to 10 Earth masses, rocky things, maybe things are living on these super Earths, who knows. And so here's an example. Here's a radial velocity signal. So we look at we've got days on the x-axis. How many days? 51. Now these are funny, these Julian days, so it's a funny, but 1,005, so there's 500. So this is a long period planet that they're measuring, they're detecting here because they can see this sinusoidal thing. You see that it's not a perfect sinusoidal, it's got a bit of a wave on top of it. That tells us that there's something even further out with an even longer period. And we see the signal is of the order of 50 amplitude, 50 metres a second, like 51 peg, but with a much longer period. But actually, so with the data we see here, there's blue dots and red dots with error bars on them, and there's some green ones too. So Corelli, it's the spectrograph that they built on the Swiss telescope, and so that has a precision of 7 metres a second, still pretty good. But that Harp spectrograph, we can zoom in. Where am I? There. So it turns out that on top of that, superimposed on that big wobble is a little wobble. We can see it here with the beautiful precision of the Harp spectrograph, these red points. So zooming in on the green, these should be green to match. These are the green points. There's actually a little wobble. And that says there's a short period planet in this system as well. So there's 500 days or whatever it is on the big cycle. And then this thing, let's see. Oh, there it says there, 9.45 days with a mass of 10 Earth masses. So tiny compared to Jupiter. So remember, Jupiter's 300 Earth masses. So they can detect that. And now, I haven't got slides up here, but one of the other things you may well ask, well, you know, it's all very well to be able to measure the stars moving like this, but the stars themselves have got all this bubbling atmosphere and magnetic fields mucking around with the signal, and they have to correct for that as well, and that's a whole nother story. But they're getting better and better at it, and really peering into these signals and seeing the presence of low mass planets. So, well, okay, that's a little slide just indicating the relative sizes of the planets, including these funny things called super-Earths. Okay, by 2009, we knew that there were many, many more Neptunes and super-Earths and Earths than there are Jupiters and Saturns. So I showed you that plot before with the curve going up, up, up towards lower mass planets, but still Jupiter kind of planets. And now, and this is actually an old plot as well, but we now know that the further down you go in mass, the more and more and more there are of these planets. They're harder and harder to detect, but they're there. So the universe, well, the nearby universe is chock-a-block with these super-Earths. Well, we're starting to detect Earths as well, but Neptunes and super-Earths are super plentiful. And probably the little guys are even more plentiful. We just have to wait and see with those. So this is, yes, if we also know, and I made this statement right at the beginning of the talk, that at least 40% of nearby stars have planets. And actually they're just ones with their short periods. So just like 51 Peg only takes 4 days, the majority of planets that we know so far have orbital periods less than the period of Mercury. I mean, there's just zillions of these little things. Our solar system's quite special as far as we know. Well, really we don't know, because we still don't know how many stars have much longer period planets, because we haven't been searching for long enough. I mean, if you want to see a whole orbital period of a thing that takes, 50 years to go around, you've got to wait for 50 years. And so, it's early days for that. But we know there's lots and lots of these short period things. And I say to my students in my honours class, one of the reasons why the exoplanet field has exploded is because the periods are so short, you can, in the time span of a PhD, you get lots and lots of orbits, and so you can do lots and lots of work on it. If you had to wait for 12 years, well, you wouldn't have much of a PhD. Okay, so 2009 I mentioned, and this is the year that the Kepler Space Telescope was launched. So I've been talking about the radial velocity method, this wobble method, and it allows us to actually estimate the mass of the planet. Here's a different detection method. The other main, there are several others which I won't talk about, but this is the other main one. It's called the transit method of planet detection. And well, we've seen, you might have even seen the actual thing, or at least pictures of the transit of Venus, for example, across our own sun. So the idea behind the transit method is you stare at a star using that method called photometry. Basically, you're just counting photons, collecting light in your light bucket, your CCD, like in your camera, and you're counting them, and you're staring at a star and you see that the brightness is pretty constant, it doesn't change much. And what you're hoping to see is a dip as a planet crosses the face of the star and blocks out some of the light. So this is the transit. Of course, you have to have the the star-planet system edge on. So most stars, you're not going to see this happen, even if they've got planets. But, you know, there's a decent chance of you seeing a system edge on so that you can see this happening. So here is an example of a transit light curve. And we see, this is just a piece of it. So we're seeing on the x-axis, if it's a bit hard to read probably up there, it's a bit fuzzy, but it's just a time from centre of transit in days. Now typically a transit will take a few hours for a planet to cross the face of its star. So most of the light curve is missing from this. It just goes for days, depending on the orbital period. And then, so we've just cut out a piece here. So the bigger the planet, the bigger the dip in the light curve. So this is an example. This was actually the very first transiting planet discovered in 1999. This was its light curve. Well, there's two, I don't know why it's, okay, they're given two epochs, two different transits. But you can see it's kind of noisy, but definitely a dip there. So when they discovered it, they got very, very excited and got the Hubble Space Telescope onto the job. And it is out in space. It doesn't have the atmosphere to muck up the signal. And, and here is its beautiful, beautiful light curve. And there's some arrows there to indicate how big Jupiter would be if it had crossed that star. And so this planet, even though actually its mass is pretty similar to Jupiter's, it orbits the star in just 3, I think, days. And it's puffed up for reasons that, well, partly because it's sitting so close to its star, but for other reasons too, that I was involved in part of that research. Okay, and if you try and detect a Neptune crossing the face of its star, you can see the green arrow there. You don't get nearly as much of a dip. And there's Earth, you probably can't even see it up the back. It's a tiny, and I can't point to it with this, but there's the Earth, tiny, tiny, tiny little thing. So the Kepler space, that's a Hubble picture there, but the Kepler Space Telescope has discovered thousands of planets this way, and given us lots of amazing surprises that I haven't really got much time. Well, I will mention my favourite surprise in a moment. But here's the thing, the radial velocity method measures the planet mass, because it's, you know, tugging at its, with the gravitational pull, and we use spectroscopy to do that, as Michel and Didier did. The transit method measures the planet's size, because it just blocks out. It's just a simple geometrical thing. You know, you put one sphere blocks out, you know, passes in front of another, it blocks out some of the light of the star. So you can measure the radius of the planet. And if you're lucky enough to observe a system, and people have done this, I have been observing and searching for planets in Chile, so I can say we with a little W. If you can observe a system both transiting and with the radial velocity method, you can measure its mass. Well, actually with the radial velocity method, you don't know the orientation of the system. If the planet was orbiting the star face on, you wouldn't see any radial velocity effect, because there'd be no motion towards you. It'd all be just, you know, transverse. But you need it to be at least at some angle that's not face on to measure the motion towards and away from you, to pick up that wobble. But if a planet transits, you know that it's actually edge on. So you know the actual mass. If you don't know the inclination, there's this factor involving the inclination that's unknown. But so if you can measure the mass and the size, the radius, the diameter of the planet, and that, of course, once you know the mass and the size, you've got the mean density. And this tells us something about what the planet must be made of. At least, whether it's a gas giant like Jupiter, puffed up, or whether it's a rocky thing like the Earth or these super Earths, or something in between like Neptune and Uranus. So the Earth has a density, a mean density of 6 grams per centimetre cubed. Sometimes people talk in kilograms per metre cubed, but that's like this great big, it's harder to visualise. In astronomy we use these grams and centimetres. So 6 grams per centimetre cube, you can imagine picking up a rock, typical rock, centimetre cube, little block, 6 grams. Jupiter is 1 gram per centimetre cube on average, much denser towards the centre, much less dense on the outside. But these numbers tell us something about what the planets must be made of. I'm just about finished. One beautiful result from Kepler and from the radial velocity surveys is they are telling us the same thing about the distribution of masses and sizes. They are both telling us that the smaller the planets, the more plentiful they are. So there's lots and lots and lots of us out there, Earth-mass planets. They're the hardest to detect, and we're getting more and more of them. They got quite a few with the Kepler Space Telescope. But really the Holy Grail is to detect an Earth around a sun-like star at 1 astronomical unit and in the habitable zone, and we can, speculate on... Well, actually, I should say that one of the offshoots of all this is to study the atmospheres of planets. So far, we can only do this with gas giants like Jupiter, but you can actually look at the chemical species in the atmosphere as the planet passes in front of the star, and in fact, when it goes behind the star and there's an absence of light, we can say something about that already. Just about finished. Okay, so my favourite discovery, it wasn't my discovery, of Kepler, was the multi-transiting systems. So just, the solar system is pretty flat. The planets are all pretty much in the same plane, but there's little tilts between them of a few degrees. And if you could look at the solar system from far away, and you saw, let's say you saw Jupiter transit, you wouldn't see the other planets transit. So you wouldn't know they were there. Well, you might infer their presence from radial velocity, you could know they were there. Daniel did his honours project on partly to do with this. So he's heard it all. So these Kepler systems, it turns out, there are lots of systems, planetary systems where many planets in the one system transit. That means they're wafer thin. These planetary orbits are all in the same plane, and nature has arranged it this way, and it tells us a lot about how planets form. And this is getting close to what I do my research on. But this was one of the most exciting discoveries, certainly for me and for everybody in the field. So here is a cute little, yes, I have to use this. This is the Kepler orrery. So if you know what an orrery is, in the old days people would make these little planetary systems, and you'd wind the thing, and the little planets would go around, and the ones closest to the sun would go around fast, and then the other ones would go around slowly. Little mechanical device. So my colleague Dan Fabrici in Chicago, well, he wasn't there then, somewhere else, but anyway, he made this cute little... So these are just some of the planetary systems, relative scale. You see some of them are slow, some of them are very fast. It's this, not that. So, but, you know, I look at that and I see so much more than just things going round and round. These planets are interacting and they're like little fossil remnants of the planet formation process. And there's so much we can learn from studying these things. Okay, that's enough, Dan. And almost finally, the second last slide. And how did that bloody planet get there? I said right at the beginning, well, how did it get there? You know, I gave you a lesson on planet formation and how these things form. They need lots of ice to form, and there's no way they can form near this star. And the answer is, and we had some understanding of it already, and Bernard mentioned my colleague Doug Lynn in Santa Cruz certainly understood how this worked back then. So he was very excited when 51 Peg was discovered. And the answer is, so you've got these planets forming in this disk of dusty gas. And they're getting bigger and bigger, more and more massive. And so they raise a tide, you know, they disturb the disk. And that disturbance acts back on the planet and pushes the planet in or out. So it's a tide. It's like, you know, the moon raises tides on the Earth and so on. It's a disturbance. And so we now understand that this is the process that moves planets around. Now, solar system, Jupiter and Saturn are happily far out, somewhere near where they formed. They probably moved a little bit, and we don't fully understand why they didn't move much, and lots of these other planets moved hugely. And there are other ways. This is just one way to move a planet. There are other ways involving gravitational interactions that are close to what I work on, but this is probably the main way. So yes, it's all okay. 51 Peg is allowed to be there according to our theories. And this is my last slide. The discovery of planets around other stars has forever changed our understanding of the universe. So it really, really, really did deserve this prize. Some physicists may feel that it wasn't, I don't know, intellectually as challenging as they would like to have a prize given to, but nonetheless it really has revolutionised science. And so cheers to Didier and Michel.
So if light travels at a constant speed, and so the further you look, the younger the universe is that you're actually observing.
Right.
And if I assume that the early universe had a lesser abundance in heavier elements, is there a cutoff distance where beyond which there's no point in looking because chances of finding an Earth-like planet would be basically?
Okay, that's a really, really, really good question. First of all, the simple answer is we can only see planets around very nearby stars. So we're not seeing anywhere back in the universe like it's just today, you know, okay. But if we were able to do that, this is a good question, and certainly people in our department think about stars forming in the very early universe and how they could have done it without all the elements that are available to more recent stars. So yeah, this is a question. And actually a related question, in fact you don't have to look so far into the past to see ancient stars that were formed very early on. Globular clusters contain very old stars, and there have been continuing searches for planets in globular clusters. There's another thing about them, though, that the stars are very close together and they go around, you know, bumping into each other even sometimes, and that may really wreck or, you know, upset the planet formation process. So that, but excellent question, yeah. Oh, yes?
We can see 40% of the stars which have a planet to it. Why can't we see the planets with it?
Why can't we see the planets
with the stars?
So I'm just, so the question is, if we can see 40%, ask me the question again and I'll try.
If we can see 40% of the stars
If we can see 40% of the stars
in the universe,
in the universe
with planets,
with planets,
why can't we see the planets also?
Visually.
well, why can't we see the actual planets?
Yeah, why can't
Yes, because it's like that picture I showed before with the big lighthouse. Did you write to me the other day? Was that you? Sorry. Oh, no, it's somebody else. Okay, so the star is super, super, super bright, like that lighthouse I showed, right? And the planet has just got a little, it doesn't even shine all by itself. It's just got a bit of reflected light shining off from the star. And the planet's so tiny, it's just a little poof, like the little firefly. So it's just, the star is just blasting it, you know, we can't see. But there are some planets, the baby planets, very young planets that are still a little bit bright, but as long as they're very far from the star, we can kind of see it. We can block out the lighthouse, the star, the bright star, and try and see little pinpricks of light far out. Yeah, excellent question.
There was a program on TV a while back with Brian Cox out in Australia,
Yep.
up in the middle of Australia sort of thing, and they had a data package, there were other astronomers with him, they had a data package of observations like you're talking about, which they released to the general public as far as I could work out. And within the space of the program,
Yes.
they'd come back with, well, there's that star you're looking at, it's got 12 planets rotating around it. I think it took a couple of days to do
Yeah.
They must have some pretty sophisticated software out to the general public to do that.
Yeah, well, this is, I don't know exactly what they put. I remember that because one of the discoveries was right up my alley. I got very excited about it. But, you know, they have, what do they call the science that... Citizen science, yes, that's right. And for example, they get people to look at pictures of galaxies and classify them. The human brain is still much better than a computer, and we see patterns really well. And I can't remember exactly what they were looking at transit light curves, I think.
Yes.
So you know, like I showed you before, a beautiful, obvious example of a transit, and exactly, yeah. So if you've got more than one planet going around, what you're looking for is, well, if you just have one, you see dip periodically. But if there's more than one planet, then there'll be another one with a different spacing, and sometimes they're even on top of each other. Not the planets aren't physically, but they're in front of each other. And so they were getting human eyes to stare at these light curves and try and see dips. Because, you know, the Kepler and other transit surveys, they have an automated search algorithm that tries to look for these things, but they have to have little rules that may miss some. You know, they have to have a cut-off. Okay, the dip has to be this much. But yeah, I mean, you know, the human brain is...
One of the guys that came on, Brian Cox, said to him, "Oh, you're an amateur astronomer," and he said, "No, I'm a motor mechanic."
Oh yes, that was the guy, he discovered a system of, it was a chain resonance. Oh yeah, my favourite delicious thing that I'm working on. And so this is, and actually I'll say, you know, I just said, chain resonance, what the hell's that? These planetary systems are like little molecules, right? You've got a star, it's like the nucleus, and the planets going around like electrons. Well, but the thing is that molecules, or let's just say an atom, right, a nucleus with electrons going around, they're in very definite spacings, little orbital spacings and energies. This is quantum mechanics. Now, gravity isn't supposed to be like that. I mean, whatever that means, isn't supposed to be, but it's not quantum-like. I mean, you know, but it turns out that it is kind of like that in a lot of cases. This is what I work on. My family just can't get any of my time because I'm calculating. But it's, and gravitational chemistry is my life's work. Thanks.
I wanted to see an article
You
NASA
speak up a little,
actually going
Barry.
back a few years ago.
Yeah, you saw an article a few years ago, yeah?
Of the 300 billion stars in our galaxy, there could be as 3 billion planets like the Earth or in the habitable zones of stars like the Sun.
Oh, yeah.
Yeah. The trouble is, the nearest one's so far away, forget about it.
No. Oh, well, no, that's not necessarily true. So Barry said he saw an article that suggested there could be billions of planets, Earth-like planets, in the galaxy, in the Milky Way galaxy, in the habitable zone of their stars. But he said, but the nearest one so far away, forget about it. Well, it almost certainly isn't. And actually we already have some low mass planets in their habitable zone. They tend to be around very low mass stars because we can detect those more easily, well, in the short periods. But, you know, so I'm saying, so there are lots of, the most common stars in the universe are much less massive, well, let's say a tenth of, as massive as the Sun. Just like the planets, there are lots more little guys. It's like on the beach, there's lots more little rocks than big rocks, right? And so, what was I saying about? Oh yes, the little stars, that's right. So there's lots more of these things called M dwarfs, and so the habitable, and they're much less luminous, they're much less hot, you know, relative at a certain distance. So the habitable zone is very close to the star, and so the planets that are orbiting at those distances have short periods, and they're much they have a bigger effect on the planet, so they're easier to detect. So we've got those, but there will be zillions of us around there nearby, Barry, and we just have to find them. They're just damn hard. I told you, 9 centimetres a second. Come on, this is just crazy. Hi, Simon.
So those M-type stars, are they easier to perhaps find the moon around? A juicy sized moon?
A juicy sized moon. Well, are they easier to detect a moon? Yeah, I guess in the sense, okay, so these stars are smaller. In fact, they're about the size of Jupiter, these M dwarfs. And so if you had a normal sized moon like, normal, whatever that means, a moon like ours, yes, it would make a bigger relative dip, as it transited than it would if it crossed a star like the Sun. So yeah.
With the new very large telescopes coming online in Chile and things like that, is there an expectation over the next couple of years that we'll be able to know a lot more about exoplanets? Or is it more of the fact that the larger diameter telescopes, it's sort of a diminishing returns, it's not going to give you that much more information? Or what's your thoughts on that?
Okay, so the question was about the new large telescopes being built. Well, in particular, they have a lot more light gathering power. So, and you can do, and the instruments they're building for them are higher and higher precision. A big problem with the big telescopes is that everybody wants to use them. And one of the really important aspects of this whole story, I'll ask you next so you can give your arm a rest, okay? A really important aspect is that these telescopes I was telling you about were dedicated, or some of them were dedicated to planet searching. And so they could use lots of time on them. And in particular, the Geneva team, because they built these instruments, they got what we call GTO, guaranteed time observations. They got lots and lots of nights per year, so they could look and look and look at the same stars and try and detect the presence of these things, and also figure out their orbital periods and so on. And so with these beautiful big telescopes, you know, you're not going to get all that time. However, what they're going to use them for is with these other surveys that discover this or that planet, they, you know, every now and again we get a beautiful cherry. I mean, some amazing new system, or very close or whatever. And we can use these big telescopes to stare at that particular thing we already discovered, to try and study its atmosphere, for example, and so on. So not so much time intensive, but beautiful instrument necessity to be able to ask questions as long, you know, for example, are there signs of life in the atmosphere of this planet, of this rocky planet? We look for oxygen. The Earth didn't have much oxygen in the atmosphere originally, and life established itself somehow, and then the atmosphere of the Earth became very oxygenated, and this is... So that's an example of what we'll be able to use those amazing telescopes for. And I was going to ask you, yeah.
Do exoplanets have moons?
So, excellent question. Do exoplanets have moons? And this is the $64,000, if you're old enough, question. That doesn't sound like much now, does it? 60, oh, well, what more than that? Okay, so we are still searching for moons. Tiny things. Simon asked up the back about moons. So what people try and see, a planet crosses the face of its star, and we see the dip we saw before. And then we try and see if there's another little wiggly dip on top of the dip that shows a moon going past as well as the Earth. So it gets complicated because the moon's going around the planet and the planet's going around the star, and you want to try and pick that up. So whoever gets that will be very, very happy, but we haven't done it yet. Might be you. Could be.
The exoplanets they're finding, are they largely within the Milky Way, or
yes.
looking beyond?
No, that's a really good question. Yes, they're almost exclusively nearby in the backyard.
Yeah.
Say within 100, well, you know, a few hundred light years, a few hundred parsecs. But there are some much further away. So the Kepler telescope, space telescope, stared at one patch of the sky. They picked a patch that wasn't too crowded, as we say, too many stars, but enough stars towards the centre of the galaxy. And so, the inverse square law, most of the stars are very far away, so they are seeing some really far, detecting planets around quite distant, but still, you know, on this side of the galaxy, not all that far away. So as for other galaxies, you know, that's, I'll be dead by the time they detect anything like that.
Yes. Is there any chance that radio astronomy could be used to detect planets around radio stars with the development now of these large square kilometre arrays and huge radio telescopes?
Okay. All right, so Alex gets to have a say. So the very first exoplanets discovered in 1992 were discovered with the radio telescope, looking at pulsar. And if you know about pulsars, these rapidly spinning dead stars, neutron stars, and they spin with such a precise period that anything that's mucking around with it, like a planet going around, mucks up the timing or changes the timing, and that's how they discovered the actual first exoplanet. That's those radio astronomy. Well, Bernard, what can we say about radio astronomy and exoplanets? You know what people have got plans.
I'm not an expert on that, but I think
you know when people write proposals.
That is everything. Yeah.
No, people write proposals for all sorts of things in astronomy and in all the sciences, and exoplanets, a sexy kind of thing, so they chuck that in somehow or other, and so probably the square kilometre array's got it in there somewhere. But yes, I don't really know actually. Huh? Okay. Yeah?
Oh, sorry. So I kind of have a bit of an ignorant question.
No, you're not allowed to say that in my class. No question is silly or ignorant.
I have that astronomy background, but I was fascinated to learn about how the stars rotate. I wasn't aware of that fact. So every star in our universe rotates.
Yes.
Planets are rotating around an unstable star. Is that
An unstable star. No, well, they're happily. Well, it's like an ice skater. So the star formed from some cloud that was slowly just moving. But as it shrunk, it's spun up and up, and yes, and actually the sun would have been spinning very fast, or much faster anyway, than it is now. It spins every 20-something days. I never remember exactly what they were. 27, is it? Yes, 27 days. And so everything moves in the universe. You look up in the sky and there's just some pinprints of bricks of light around. They just look like they're just sitting there. But they're all moving with huge speeds. And the Earth moves around the sun at 30 kilometres a second. Did you feel it? Oh, we can't feel that. Right, the Earth spins once every 24 hours. Holy moly, when you think about it, that's a lot of spin. Mm-hmm. And the moon's orbiting there, and the sun is flying around the galaxy at 200 kilometres a second. And we're going around the sun as it goes. Everyone's going for a ride, and all these stars are going around the Milky Way on the big race course. Yes. Well, no. Yeah. The Earth, the Earth's going around the sun, and the sun's going around like that. Yes, and the moon's going around the Earth. Everybody's going around everybody. Yeah. The Milky Way is moving through the universe,
Yeah, light's not really like sound waves, so whether it's coming towards you or away from you, it arrives at the speed of light.
That's right.
So why do you get a Doppler effect?
So it's about the energy. He's asking me, why does the Doppler effect work with light waves?
The waves shouldn't bunch up because it's going away or coming towards you. It's still arriving.
Well, it affects the frequency,
but why?
Not the speed.
Well.
Bernard can answer the question better, but it's about the energy of the.
Mm-hmm. Well, it's actually a tough one.
Oh, thank God.
That's, I think, really a tough one. And, the point is, Rosemary, is true, the frequencies change, and that does mean that you see the crests of the waves actually bunching up. But this speed of the crest of the waves, that is not really the velocity at which the photons, the particles of light, travel. There's a difference in physics between this velocity of the wave crests, which is an apparent velocity, right? So if you
but it's like a cork on a
exactly that analogy.
Yeah, but
right?
they're not relativistic though. Light is. Light shouldn't bunch up, should it? You're comparing them to physical things, which are different. They're different. Like if two cars travel together at a certain speed, they're additive or subtractive or whatever. But light's not.
No. Well, yes. It's go on.
I think it's absolutely true. I think the key difference is to recognize that the speed of the particles, it's really different from the speeds of the electromagnetic wave crests, electric field and magnetic field going up and down. Very much like this example of water waves that Rosemary was referring to. What you see is the pattern, the spacing of the wave crest, and that changes when the source of the electromagnetic radiation moves. And it's not because the speeds of the waves move.
It's not that. Just a layperson's understanding of this. If light's composed of not just one frequency, it's composed of just a vast spectrum of sine waves or whatever. So the relative shifting of those sine waves may change. The actual speed of them won't. So it may appear as though there's bunching going on.
No, but even if you had just one frequency, this would happen. The frequency would change, but if your source of light was one frequency, and you'd see well, if it's just sitting there, you'd measure a certain distance between the wave crests, and if the source moves, it kind of bunches the wave crests up, but the speed is still the same. But it's still, the same thing would happen with just one frequency. But yeah, good possibility. Can I, before I'm going to take your question, but I want to know if Joseph is here. Is Joseph? My man, you were sitting under my nose. I'll meet you afterwards. Yeah, okay. Sorry, yeah.
The gravity can bend light, and you have to take that into account in your observations?
Well,
just too small to...
No. However, general relativity, which is behind that, it does have to be taken into account in our calculations. People need to go. Yes, but so not the bending of light, but certainly relativistic effects do need to be taken into account. Look, thanks for coming, everybody. I really appreciate you coming out here to Monash.